we're really glad to have Dennis Sudakov from ETH, and he'll tell us about rainbows and Latin squares and much more. Go ahead.
Okay. Great. So thank you very much, everybody, for coming. Sorry for technological problems. So I want to talk about several results which I got over the last 3-4 years, which I think makes a very colorful story. So a Latin square, so let me start with the definition, is n by n array, which is filled with n symbols, where each symbol appears precisely once in every row and column. So you're probably familiar with the Latin squares from Sudoku puzzles or, multiplication tables of any finite group. So if you take a table, you get a Latin square, but Latin squares appears also in the design theory, in finite projective planes, in error correcting codes, two-dimensional permutation, to name just a few. So when you're talking about Latin square, an important object is a transversal. So transversal in Latin square, it's a collection of n entries which appear in different rows, columns, and contain n different symbols. Like, for example, this green thing on the screen, it's a transversal in Latin square. So the study of transversal in Latin squares goes back quite a lot in the past, more than 200 years, to the question of Euler, where Euler asked which Latin squares are there Latin squares which can be decomposed into disjoint transversals, right? So let's see an example. So here is a Latin square which I had before, and this green color is the first transversal, which I can find in this Latin square. But then I can find a purple transversal, which is disjoint from green. And then I can find blue, yellow, and white transversals. So I found 5 transversals which decompose this Latin square. So actually, the question of Euler was a little bit different. What he wanted to find a so-called orthogonal Latin squares. So this a pair of 2 Latin squares, such that if you superimpose them, you get n squared different pairs, right? One entry from first transversal, one entry from the second transversal. And you want these entries to be all distinct. So you want to get all possible n squared pairs. And one can show that this question about decomposing Latin square to transversal is completely equivalent to the finding a pair of orthogonal Latin squares. So again, let's do this. So I showed you on the previous slide a Latin square, which was decomposed into transversals, into disjoint transversals. So what you can do, you can take an empty square, and then you look on the first transversal, which was green, and instead of these numbers 1, 2, 3, you put all ones. Note that this is legitimate because these 5 entries, these 5 squares appears in different rows and in different columns, so I allow to put there 1. And then I take another, my yellow transversal, and I put here all 2s. And then I take another transversal, purple, and I put all 3s. And then I take the blue one and I put all 4s. And finally, in the white one, I put all 5s, right? So I got another transversal. Now, if you see what happens when I'll superimpose them, so here's my first transversal. So when I put the other one near him on the same kind of set of squares, I get n squared different pairs, which exhaust all possible pairs ij, where I and j runs from 1 up to 8, right? So the question of Euler was when you can find an orthogonal pair of Latin squares, which is equivalent to decomposing Latin square in the triangle. So to finish this story, Euler conjectured that for every n which is not 2 mod 4, you can find a pair of orthogonal Latin squares, and otherwise you cannot. And indeed, he proved his conjecture. So he found a construction of orthogonal Latin squares for every n which is not 2 mod 4. And then it took quite a long time until in 1901, Terry proved Euler's conjecture for n equals 6. So he showed that for n equals 6, there are no pair of orthogonal Latin squares. But then later, the conjecture of Euler was disproved, and for all other values, 10, 14, 18, people do find a pair of orthogonal Latin squares. So following Euler, there is a lot of research done about finding transversal and Latin squares. So for this talk, I would be also interested in the notion of partial transversal So partial transversal is just a collection of entries which stand in different rows, columns, and contain different symbols. So when I want to say that my transversal has n elements, I will say full transversal or just a transversal. So following Euler, it's a natural question to ask which Latin squares have a transversal. Okay, so it's very easy to come up with construction of Latin squares which do not have transversal. So for example, take an addition table of the group Z4, residues mod 4. So if this group would have if an addition table of this group would have a transversal, look what we can do. We can add all the entries of this transversal. So then we'll get sum of all elements in Z4, which is 2 mod 4. But because it was these entries were coming from addition table, every entry was a sum of 2 other entries. So the same sum should be equals twice itself. And obviously 2 mod 4 and 4 mod 4 are different numbers. So therefore, this is impossible. Actually, even answering this question for addition tables of the groups appears to be quite difficult. So there is a conjecture, there was a conjecture, it's now solved, by Hall and Page, who in 1955 proposed a characterization of all the groups whose addition table has a transversal. So they said that transversal exists even only if 2 seal of subgroup of this group is either trivial or non-cyclic. And it took about 50 years until Wilcox, Evans, and Bray in 2009 proved this conjecture. It was quite a non-trivial proof because it's used a classification of finite simple groups. Recently, in 2020, a very nice different proof, at least for large group, was found by Eberhard, Manners, and Brazovic. But even this proof is quite non-trivial. It's like a 60-page paper with a lot of use of heavy analytical number theory. So I want to talk about a combinatorial setting. So a kind of central conjecture about transversal in general Latin squares is the following conjecture of Reiser and Braldi and Stein, which says that if you have a Latin square and n is n by n Latin square and n is odd, then this Latin square has a full transversal. And if n is even, then it has at least transversal of size n minus 1. Okay? So there's still an open conjecture, but over the years, people try to find a larger and larger transversals in Latin square. So they try to come up with a partial results. So let me mention some of them. So the first result was proved in 1969 by Koxma, who proved that every Latin square has transversal of size at least 2/3. Then this was improved by 3/4 of n. And the first asymptotic result was proved by Woolbright and Brouwer and De Vries and Wieringa, who showed that every Latin square has transversal of size n minus square root of n. And the best result until recently was proved about 30 years ago by Peter Shor, who showed that there is always transversal of size n minus constant log square n, which is very close to already full transversal. So original proof, this is why I give here 2 names. So original proof of Shor had a certain small bug in it, which was later rectified using the same ideas by Hatami Shor. So our first result, which I want to present, is improvement of the Shor's and Hatami Shor's bound. So what we can prove, we can reduce the error term to roughly to a square root of the original one, roughly to log. So our proof, right, I will want to say that our proof is very different from that of Shor and Hatami Shor. It provides a reasonably general framework to attack not only Reiser conjecture, but several related problems as well. And I want to talk a little bit about these problems. By the way, needless to say, please stop me and ask me questions if you have one, right? So let me extend a little bit the notion of Latin squares to so-called Latin arrays. So Latin arrays are very similar to Latin squares. You take n by n array, you fill it with symbols such that symbols appearing in the same row and column are all different, but you're allowed to use more than n symbols. So for example, you can get a lot of examples of Latin array if you take an arbitrary group, two sets of n elements, and you take multiplication table of products between them, right? Obviously, you get a Latin array, all rows and columns will contain different symbols, but you might have more than n symbols. So when you're talking about arrays, a natural question is, do extra symbols help you to find the transversals in Latin array? And obviously, natural feeling is that they do. Okay. So such results were obtained over the years for Latin arrays which are far from Latin squares. So for example, Erdős and Spencer proved that if you have a Latin array where every symbol appears at most n over 16 times, then you have a transversal. Stronger than that, so it was a question. Stronger than that, oops, sorry. Alon, Spencer, and Tatterley proved that if every symbol appears at most delta n times for some small delta, not only you can find one transversal, but you can find many disjoint transversal. You can decompose almost Latin square in a Latin array into disjoint transversals. So the next result, which I want to present, strengthens this in the following sense. Right? You can read the numbers, but let me tell you what it basically says. So you look on your Latin array, and then obviously, because it's array, every symbol can appear at most n times. So you look on symbols which appear almost n times, right? And you count how many of them you have. Now, for example, in Latin square, you have n symbols appearing n times. So if you look on symbols who appear very close to n times, and their number is slightly smaller than n, so it's enough for me to have n minus n to the power 1 minus epsilon such symbols, already this guarantees you that you can have a transversal. And moreover, in this case, you have almost decomposition into disjoint transversal. So basically, roughly, if you want without numbers, what it says that the only Latin arrays which have no transversal are very small perturbation of Latin squares. The minute you slightly away in any distance from Latin square, you always have a transversal. You even have a decomposition into transversals. Okay. So another question, which I find very interesting about Latin arrays, is the following question of Akbari and Alimpur. So they ask, given a Latin array, how many symbols it should have, just that from this sheer fact that it has many symbols to guarantee a transversal. And in particular, they ask, are there n square over 2 different symbols enough, right? If it has half of the different symbols, is this enough? So the result which I showed you on the previous slide allows you to prove to answer the equation in the following strong form. So from the previous result, it follows that Latin array, which has n to the 2 minus epsilon symbols, already has a transversal. So a different proof of this. So you can use our result with Richard and Alexei. A different proof of this result was obtained independently by Peter Kivash and Liana Yepremian. So we decided to join forces and improve it even further. So what we managed to prove is that Latin arrays, which already have roughly n log n different symbols, must have a transversal already, right? So if you have n log n different symbols, you have a transversal. So an interesting aspect of this question of Akbari and Alimpur is that if you have a very good bound for this question, it already implies a good bound for Reiser's conjecture. So let me show you this simple connection, right? So imagine you know our result with Peter, Liana, and Alexei. So you know that every Latin array with n log n, say, distinct symbol has a transversal. So let me give you a bound, or let me show you that any Latin square has a large transversal of almost size n minus constant log. Right? So what you do, you start with your Latin square and you delete symbols in the first log n over log n rows, and you put there in every square a new symbol, and you put it exactly once. Now what you got, obviously, you didn't destroy the properties of array, so you got a Latin array. And this Latin array by construction has n log n distinct symbols because you put them there. By the above result, by this result, this Latin array should have a transversal. Now look on this transversal. This transversal can use at most, because it takes one symbol from every row, can use at most log n over log n symbols from first log n over log n rows, right? And these were fake symbols, so I obviously cannot take them into account. But if I remove them, the rest is genuine transversal of the original Latin square, and it has size n minus constant log n over log n. So this shows that at Barry-Alickpur equation, if you prove a good bound for it, it's actually a more general equation than proving good bounds for Reiser conjecture. So any questions?
Benny, so you told us about the difference between Latin arrays and Latin squares.
Mm-hmm.
But if Reiser's conjecture is true precisely, then there is no difference, right? If every, for example, odd Latin square has a transversal, then
no, it's not true. It's actually a very good question, Avi. So actually, Latin array on a small scale, they can have worse properties than Latin square. So you can construct Latin array which will not have a transversal of size n minus 1. So the fact that obviously it will still have a very large transversal, but you can spoil things by having different symbols. It's not that you can reduce Latin array to Latin square.
No, but asymptotically.
Asymptotically true, of course.
Yeah.
Asymptotically
they may have the same properties exactly.
Right, but they definitely different objects. And as I said, right, since we don't know Reiser conjecture, one way to attack it, for example, would be to show that any Latin array with big constant n symbols already has a transversal. This will give you the bound n minus a constant for Reiser conjecture by the reduction which I just showed.
Right. And you believe Reiser conjecture?
I do believe now Reiser conjecture.
Okay.
Definitely, I do believe n minus a constant.
Okay.
Right? I don't know if n minus 1, but I definitely do believe n minus a constant.
Thanks.
Yeah. So let me now move to a little bit different object, Steiner triple systems. So what is a Steiner triple system? So given an n vertex set, I want a collection of triples which cover every pair of points exactly once. Right? So let me give an example. So suppose you have 7 vertices. Here they are. So take this triple, right? I drew you triangle, but think about this as a hyperredge, right? Steiner triple system is a 3 uniform hyperredge. Right? Think about this hyperredge, 1, 2, 4, and then shift it cyclically around the circle 7 times. So you can check that the hypergraph which I draw you has 7 triples, and they cover every pair precisely once. Actually, Steiner triple systems are very fascinating object. In particular, the sporadic simple groups appear as automorphisms group of specific Steiner triple systems. So they appear in other places of mathematics as well. So the study, right, of the Steiner triple system, and the name goes again quite back to 1853, where Steiner asked for which n there are such triple systems. But actually he didn't realize at the time that some number of years earlier his question was already answered by Plücker and Kirchmann, but somehow in the literature the name Steiner triple system remained. So let's say a few words about the existence of Steiner triple system, just kind of to see what we're dealing with. So the first, Blücher observes that the necessary condition for existing a Steiner triple system of order n is that n should be 1 or 3 mod 6. So what is the reason for this? So first observe that we have n choose 2 pairs, and every triple covers 3 pairs. So we better have 3 divide n choose 2. Another thing which we have is that every point belongs to n minus 1 pairs, and every triple which covers this point will cover either 2 or 0 of them. So we also need to have 2 divides n minus 1. So these two conditions together gives you n equals 1 or 3 mod 6. And then, so this was in 1830, and then in 1847, Kirchmann proved that these conditions are also necessary, right? So basically, for every n which is 1 or 3 mod 6, there is a Steiner triple system. And it's not, I mean, I'm sure you heard about difficulty of constructing general designs, but this is not as difficult question of Steiner triple systems. And it's not hard to come up with a construction of Steiner triple systems. So let me give you one. So imagine your n is a power of 2 minus 1. So you can take a vector space of g of 2, right, z2 to the m, and you can delete 0. And then you can take your triples to be all the lines, x plus y plus z equals to 0, where x, y, and z are distinct. So you can check that these lines give you a Steiner triple system. And in general, one should say that this uniform hypergraph Steiner triple system gives you a very rich class of objects. So in particular, this is just one example, but if you fix your n on n vertices, you have roughly n to the power constant n square different Steiner triple systems, right? So it's a very rich class. So there are a lot of questions about Steiner triple systems. So in particular, one which interests me in the context of Riser conjecture is the following question of Brouwer, which was posed about 40 years ago. So Brouwer conjectured that every Steiner triple system has nearly perfect matching. So let me remind you, right? This is a 3 uniform hypergraph. So a perfect matching would be a collection of disjoint triples which cover every vertex exactly once. So then I will need to have n over 3 of them. So Brouwer conjectured that you have almost that many, right? In every Steiner triple system. Now, to see the connection, why I mentioned the riser, to see the connection, observe the following thing, that you can think about Latin squares instead of as how I define them, you can think about them as 3-partite, 3 uniform hypergraphs. Right? So what you do, you take 3 parts. One part would be rows of your Latin square. Another part would be columns. There are n rows and columns. And the third part would be symbols. And then every entry of Latin square give you a triple corresponding row, column, and a symbol which stands in this intersection of row and column. Okay. Now you see that this hypergraph also has a property that every pair of vertices between the parts covers precisely once. And moreover, the transversal, which we were interested, will correspond to a perfect matching in this hypergraph. So Riser conjecture says that this particular hypergraph, which I just defined, has a perfect matching if n is odd, and has a matching of size n minus 1 if n is even. Okay. So again, Brouwer conjecture is very much open. And again, people try to obtain partial results towards this conjecture over the years, right? So first, they proved that any Steiner triple system contain a matching of size roughly 2/9 n. Right? You remember we're aiming for n over 3, then for n over 15. Then the first asymptotic result was proved by Brouwer himself. So he proved that there is a matching of size n over 3 minus constant n to the 2/3. And until recently, the best result was proved about 22 years ago by Alon, Kim, and Spencer. So they proved the more general result, which in particular implies that Steiner triple systems have a matching of size roughly n/3 minus square root n polylogram. And so what we can do using our machinery, we can prove that Steiner triple system have a matching of size n/3 minus roughly log, right? So very similar bound as we have for Reiser, and not surprisingly because the machinery is also very similar. Okay? So far I told you some results, and I never mentioned the word rainbow, right? So it's a good time to make a connection to coloring and to rainbow problems. So here is a connection. The connection. Sorry, Avi?
Just yeah. I'm just wondering, are you going to give us some hints about how?
I will give a little bit of hints, but I should say that since I want to make a kind of a nice story, I would not give so much proofs, right? I can maybe later kind of informally talk about this. You see, right, why I'm choosing more to tell you about results than proofs, because I have some kind of reasonably long story to tell.
Okay, no problem. You are the boss.
Right. So, but let me first go to the rainbow, right? So what is the connection with rainbow? So look on this Latin square. Now, instead of different numbers, I used colors for the symbols, right? So Latin square you can think as a colored square where every color appears exactly once in every row and column. So I take, instead of this Latin square, a complete bipartite graph. So one side of this bipartite graphs would be columns, one side would be rows. And now you look, for example, on the squares of the red color, and you look on the corresponding edges, like between 1 and A, 2 and B, 4 and C, and 3 and D, and you color these edges of the complete bipartite graph red. And then you do the same with the color blue, with the color green, and with the color yellow, and you get a properly colored, right? Because the fact that every row and column contain different colors means that every vertex there are edges of different colors. You get a properly edge-colored complete bipartite graph for every Latin square. The number of colors would be precisely n, and if you take a Latin array, the number of colors can be more than n, so you can just get a properly edge-colored complete bipartite graph. And now what happens with a transversal? So to look on these three squares which have different colors. So if you see a corresponding edges on the complete bipartite graph, you get a matching because they stand in a different rows and columns, and this matching would be rainbow, right? So therefore, the Reiser's conjecture, you can be reformulated in the following language. So if you take any properly edge-colored complete bipartite graph using n colors, right? The coloring has n colors, then the conjecture says that you can find a rainbow matching of size n-1. And for example, the result we prove with Alexei, Peter, and Liana says that every properly n-edge-colored complete bipartite graph has a rainbow matching of size n minus constant log n of n. So as I said, unfortunately, I will not go too much into the proof, but I don't want completely disappoint you. So let me give you at least something. So I use this slide to give you a bird's eye view of our ideas. So let me start with the lemma, which I think is interesting for its own right. So the lemma says the following. Start with arbitrary bipartite graph, which has parts of size n, whose degrees are not very different. So they're roughly the same up to a constant. Let's say the degrees are constant times d. And then choose a random matching by choosing every available non-edge in this graph, randomly and independently with tiny probability, epsilon over n. And then obviously you might have some edges which intersect, the edges which intersect deleted. But you will have very few because I'm choosing my probability to be epsilon over n. So this M0 would be essentially a matching modulo some small deletion. Now what lemma says that no matter which graph you started with, obviously it can be very, very disconnected. If you add to it this random matching, it will become a good expander in a very kind of precise way, which I can quantify, but I will not do this in this talk, right? So arbitrary bipartite graph, you add a random matching, it becomes an expander, and it becomes with pretty high probability. So how you can use it? So here is basically what we do. You start with your NH colored bipartite graph and use it. Then you use a standard technique called semi-random method or Rodel-Nibel to find a rainbow matching which is nearly spanning, but it's far from what we're trying to prove. It's at size n minus n to the power 1 minus epsilon. So you find a pretty large rainbow matching, but because you use a random technique, it would be, big chunk of it would be random. Big chunk of it will look like M0. Then you look on the colors which do not appear in the matching, right? You call the union of these colors H. So obviously, because this is a kind of NH colored complete bipartite graph, every color is a matching. So perfect matching. So your H would be nearly regular, right? So then you observe that no matter which, say, D colors you took, because this high probability is pretty high, you can take union over all subset of roughly log n colors and deduce that any H which you get like that together with this M would be an expander. So then you can use, right? I didn't quantify you this expansion properties, but now I will. Then you can use this expansion properties to show that this union will contain a rather short path. Short for me would be logarithmic, actually would be log n over log n, path, which starts with the edge of H. So start in a color which I don't yet have, and then alternate between edges of H and M, and ends again in the H which has color from H, which is a color which I didn't use so far. Then obviously what you can do, you can use this alternating path to switch edges of the matching to the edges of non-matching. And because the path was rainbow, this new object which you get would be matching, which would be rainbow, and which has size by 1 bigger than M. And observe that you can continue to do this procedure as long as you have at least log n over log n unused colors. And that's kind of will give you the matching of size n minus constant n over log n. So I think if you want to take something from this talk, is this kind of simple sounding lemma, which says that you take a D-regular graph, say my D is B constant, you add every H with probability epsilon over n, clean it to have a matching just for our purposes, then the union is expanded in certain sets, okay? So any questions?
Benny, this lemma will probably hold also for D equals 2, right?
So for D equals 2, then it would be too weak for us, but it definitely holds for D being large constant.
Yeah, but in some sense, yeah, it will be too weak for you because of the parameters, right?
Right. So basically, when I say good expander, it's not necessarily we need to be connected. I only say that large sets expand pretty well to bigger sets, right? Because, you know, imagine if you'd have a union of C4s and you add to it some random edges with probability epsilon over n, there would be plenty of isolated C4s in your graph, right? And you would not connect them. Then if your D is small, then you will have only small chunk of your graph, which would be reasonable expander. But if your D is large, then a big chunk of your graph would be reasonable expander. And then you can, in a very short walk, can reach almost everything. And that's what we're using. Actually, we're using this lemma where our D is log n over log n. And then, you know, it has expansion so that in a path of length log n over log n, you can reach almost everything. So that's where the numbers come up together.
Okay, thanks.
Right? But you're right. It just, we need it a little bit bigger. Okay. More questions?
Hi, Benny. I have a quick question. So
Right.
in M0, you take just any edge. They don't have to come from H.
Well, no.
Or they come from H.
They actually don't come from H. I take all the non-edges. Edges from H I already have.
Okay, so you take from the complement, pick them.
I take from the complement edges with probability epsilon over n. I take genuinely random bipartite graph. I mean, you can take edges of H as well, but mainly edges from non-H, right?
Okay.
And that's what fixes your graph, because your graph, as I said, right, if your D is small, if your D is 10, you can be union of complete bipartite graph K10, K10, many disjoint ones. You're not even connected. You have plenty of kind of small components, but you can fix this by just adding a random match.
Okay, thank you.
Okay. Good. So now let me kind of continue, and you'll see why I'm not showing so much proofs, because I'm actually only told you half of the story. Right. So let me go to the second half of my story. So far, I talk about finding a rainbow matchings in properly colored bipartite graphs. You can extend this question, and you can ask for other graphs, and in particular, I would be interested to find rainbow trees. And so my setting would be a little bit more general. So before I was looking at proper edge coloring. So the proper edge colorings means that every vertex, all edges touching it have different colors. Now I extend it a little bit, and you'll see why it gives me a little bit more space for more general results. I will look on K-bounded colorings. So my coloring is K-bounded if at every vertex there are at most K edges of the same color. So in particular, if you think about proper coloring is just one bounded color. For me, my K would be usually fixed, right? So what I want to do, I want to look on the complete graph on n vertices, look on arbitrary K-bounded colorings. You give me your favorite tree, and the question I want to answer, can you find this tree in this K-bounded coloring? Can you place it so that the tree, that your copy which you get is rainbow? Right? So this is a question which I want to discuss next. Okay, is it clear? So again, I'm looking on the edge coloring of the complete graph. This coloring are K-bounded, so it means that every vertex, every color appears at most K times. You give me your favorite tree, and I want to know, can I find a copy of this tree in this complete graph? Obviously, I can find a copy of any tree, but I want that when you place it there, it would be rainbow. All edges would have distinct colors.
But Benny, you may not have enough colors if you allow.
Absolutely, Avi. Excellent question. So obviously, the size of my tree would be always, so here is the first bound which we immediately get. So if I have a K-bounded coloring, I will need at least to have n over K colors. So I will not hope to embed trees of size bigger than n over K, right? N over K would be a natural bottleneck. So if my coloring is proper, I can embed spanning trees. But if my coloring is K-bounded, I can embed trees of size at most n over K. So the question is, what can I do this? Can I embed any tree, some particular tree of size n over K in such a color? Right? Exactly this is the question, right? So very good. So we're always aiming to embed trees of size at most n over K. Great. Any questions? Yes, this is precisely what I will try to achieve. But before I'll tell you what can be achieved, let me spice it a little bit for you and explain why at all, right, I would want to prove such a result. And I'll give you 3 examples which I think are interesting. Right? So the first example comes from so-called harmonious labeling. So given a tree T and a abelian group gamma, a gamma harmonious labeling is a labeling of the vertices of your tree such that when you add the values of the function over all the edges, you get distinct values, right? So is it clear, right? So you put your labels, then for every edge, you compute the value of x plus y, and you want to get distinct labels, right? So the conjecture in this area, a very old, long-standing conjecture by Graham and Sloan, says that every n vertex tree had a Zn harmonious labeling, right? So if you take a residue mod n, you can assign it to the vertices of your tree such that the labels which you get along the edges are all distinct. So let me show you. So here's a tree of 7 vertices. So I want to assign labels from 0 up to 6 to these vertices, such that the sum along the edges would be, I get 6 sums. The tree has 6 edges, would be all these things. And indeed, so I set 0 from 6, I do 1 from 7. So I can do it like that. So you will get all the distinct labels. So is it clear? Right? So harmonious labeling means assigning labels so that along the edges you get distinct sums. So, so this conjecture of Graham and Sloan draw a lot of attention. So there is a lot of papers about it. So first, there are a lot of papers which verify it for very special trees. Obviously, people know it is true for pars, stars, but many other trees as well. I want to mention also that even in asymptotic sense, this conjecture was open. So even if you allow me to label the n-vertex tree with numbers modulo a slightly bigger residue, n plus little of n, this was not known. But it was known that if you take a bounded degree trees, then you can do it. So this is a result of Adamczyk, Allen, Grosso, and Clark, right? So if you take bounded degree trees and you allow me to use labels which are slightly from a bigger group, the n plus little of n, then you can do. Now to see the connection to rainbow colorings, let me do the following. Take your complete graph, think about its vertices to be residues mod n, and color every edge of this complete graph by the sum of the value of the vertices mod n. So let's do the example. So my n is 7, and so my vertices are from 1 up to 7. So 1 plus 2 is 3 mod 7, 7 plus 3 is 3 mod 7, 4 plus 6 is again 3 mod 7. So these edges got color blue. And I continue doing coloring exactly in this manner. So I color every edge by x plus y mod n. So what I got a proper coloring of the edges of the complete graph. And now what I want to place this tree inside this coloring in such a way that the copy which I got is rainbow. And if you think, what does it mean? It means exactly that the addition along the edges produce me different sums. Okay. So this first example. So finding a rainbow copy of a tree in this particular coloring would answer the question of Graham's law. Now here you can say that if you think a little bit about the question itself already kind of sounds like a problem about rainbow copies of the tree in some coloring. So this is not so surprising, and I indeed will agree with you. So let me give you a different result where I think the appearance of rainbow trees are very surprising. And this is an old conjecture of Ringels. So what this conjecture says, it says that you take a complete graph on 2n minus 1 vertices, and you take an arbitrary tree on n vertices. And then conjecture says that you can tile the edges of the complete graph on 2n minus 1 vertices by the copy of this tree, right? So let's see an example. Obviously, it's a very simple example. So your graph would be K 5, right? So my n is 3. So I take 3 on 3 vertices. It has 2 edges. And then here I can tile this K5 by the copy of the path of length 2. Now, if you think about this, this is a pretty striking conjecture, because I'm claiming that I can do this for any tree on n vertices, right? There is no restriction on the tree. And I think maybe when Ringels first come up with it, there was not a lot of evidence for it, except that the number of edges in complete graph on 2n minus 1 vertices is precisely 2n minus 1 times n minus 1, which means this tree, which has n vertices and minus 1 edges, potentially can be placed 2n minus 1 times disjointly in this complete graph. Okay? So again, over the years, people were very much fascinated about this conjecture because it has such a succinct and appealing form. And indeed, they first verified for special trees, so you can check that it's true for paths, stars, something they called caterpillars, and many other trees. Then it was proved asymptotically by Bocher, Hladky, Piguet, and Taras for all bounded degree trees. And then recently, it was proved exactly, again for bounded degree trees, in a very beautiful paper by Joss, Kim, Kuhn, and Ostus. And observe that it's again similar to the previous problem. All the results, all the general results which we have, they require a certain bound on the degrees of trees, right? Because if the trees do not have very high degree, it's a little bit helps you in the proof. Now, what is the relation of this problem, right? There is no colors, there is not even labeling. What is the relation of this problem with rainbow trees? Okay. To see this relation, we can do the following. Take your complete, so maybe let me add one more slide. Take the vertices of your complete graph. So in my case, my n would be 5. So 2n minus 1 would be 9. So I take these 9 vertices and I put it on the circle, right? Equidistance. So things that they are vertices of regular 2n minus 1 going. And now I color the edges of the, I think that there is a complete graph there. And I color the edges of this complete graph by the distance between the point, the Euclidean distance along the circles. So let's do it. So first we look on the vertices whose pairwise distance is 1, so they are neighboring. And I color these edges by color 3, right? There are precisely 9 edges here because there are exactly 9 pairs like that, and they're all green. And then I took the vertices which distance 2 and I color them blue. And again, I get 9 blue edges because there are 9 pairs in distance 2, and I get a color green. And then distance 3, I color black. And then distance 4, I color red. In this particular case, there are no other colors. So because I have 9 vertices, every pair has distance either 1, 2, 3, or 4, because I'm taking a shortest Euclidean distance, okay? So this is my coloring. Observe that this is now not like in previous example, a proper coloring, but this is 2-bounded coloring because every color class was a 2-factor. So that's why I wanted to extend the class of coloring I'm looking at to k-bounded coloring. So in this case, I got a particular 2-bounded coloring. And now I look on this coloring and I ask, can I find this tree in this coloring rainbow? Can I find a rainbow copy of this tree in this color? And imagine I can, in this particular case I do, right? So here is a rainbow copy of this tree in this coloring. Now then what you can do, you can start rotating this tree every time shifting it by 1, like that. And observe that every time you do it, you get a disjoint tree from the one which you had before. And the reason for this, you can just look, for example, on a red, on this edge, right? So when you take your 2-factor and you pick one red edge and you start rotating it, you every time land on a different red edge. And since it happened with all the edges and your tree was rainbow, you get a disjoint collection of trees which cover all the edges exactly once. Is this clear? Right. So in this particular case, we got a really nice application of the fact that we can find one rainbow tree to pecking problem. Okay. So let me mention another similar sounding problem. Right. So this problem was posed, again, there is no rainbow here. So this is a problem of Gronau, Mullin, and Rosa. And they called it an orthogonal double colors, right? So now you have a tree whose size is precisely the size of your complete graph, right? And again, tree is arbitrary, except they have an exception. So in their conjecture, they have an exception when n equals 4, and the tree is a 3H path. But imagine if n is bigger than 4, then there is no restriction. So take an arbitrary tree on n vertices, take a complete graph Kn, and what they conjecture that you can cover the edges of the Kn by copies of this tree in such a way, right? So you will use, so the complete graph has n times n minus 1 over 2 vertices, edges. So you use n copies of this tree. Every tree has n minus 1 edges. So you totally use n times n minus 1 edges. So obviously you cannot do this disjointly, but they wanted to do it in such a way that every edge is covered precisely twice, and then the numbers image. and moreover, the two copies of different tree intersect in exactly one edge. And again, some nice design form. Is it clear? Right? So again, so let me give an example. So let's again go to K4. So my tree is a star, right? For K4, this either a path of length 3 or a star. So as I said, path of length 3 is exception. So we'll take a star, then we take a complete graph on 4 vertices. And what I want to cover the edges of this complete graph by stars of size 4 in such a way that you see every edge is covered precisely twice. So for example, this edge is red, yellow, this edge is green, yellow, this edge is red, blue, and so on. And moreover, any two such stars, they obviously intersect in exactly one edge. Okay? So, and again, what is a connection with rainbow colorings and rainbow trees? Apparently there is a connection, at least when n is a power of 2. So in this case, I need to put a restriction on my n. So what you can do is the following. So imagine your n is a power of 2 to the d. Then you can think, so let me maybe draw it. Then you can think about the vertices of, so in this case, n is 8, of your complete graph as a binary vectors of length d over g of 2, right? And then you can color the edges of this complete graph by sum of the vectors, right? You color them x plus y, by the sum, right? You take the color of the edge xy is x plus y in this vector space, right? So this gives you all green edges, this gives you all blue edges, this gives you all red edges, and so on. I obviously drew you all possible colors. So in this case, you will get 8 colors. And then again, imagine you took your tree, so your tree now need to have 8 vertices, and this is your tree. Imagine you found a rainbow copy of this tree in this color. Then you can produce this tiling, which will cover every edge precisely twice, and any 2 copies of this tree intersect in exactly one edge by taking this tree and shifting it by different vectors in z2 to the d. So what you do, you take your tree, and to all vertices in this tree, you add this vector z, so it gives you a shift, like for example, let me show you, like you do this, and then you shift it again, and you shift it again, and you shift it again. And obviously, since there are 8 vectors, you can shift it n times, and this should give you 8 copies of your tree. And then because of the properties of the coloring, you can check that indeed you will cover every edge precisely twice, and every 2 copies of the tree will intersect in one edge. So I hope this 3 example motivated for you this question, which I want to answer. So again, my question was, you take a complete graph on n vertices, you take a k-bounded coloring, and you ask what trees I can find rainbow in such a coloring. And this was motivation for us to prove the following result, which we proved about 3 years ago with Richard and Alexei. So what we showed, actually, you don't need to put any restriction on the tree. Pick your favorite tree, as long as it's slightly smaller than n over k, and as Avi already mentioned, n over k is a hard bound, right? K-bounded coloring can have at most n over k colors, because every color can be a k-regular graph. So I can have only rainbow trees of size at most n over k. So what we proved that if your tree is slightly smaller than n over k, so no matter which tree you take, you can find a rainbow copy of such tree in your coloring, right? And observe that this is the first result where, unlike the previous result, we have completely no restriction on the tree, no restriction on the bounds of the tree. And because of the connections which I described to you, this result immediately proves asymptotically the 3 conjectures which I mentioned: the conjecture of Graham-Sloan, and the conjecture of Ringels, and then the conjecture of Granau, Moulin, and Rosa. Albeit for this, we only prove it when n is a power of 2, obviously when we have a reduction. Finally, let me mention that in this generality, this result is best possible. So I've already said that obviously the tree cannot be big of size n over k, but I want also to mention that there are examples which show that the error term cannot be zero. So in particular, there are colorings, proper colorings of the complete graph where you cannot find rainbow a Hamiltonian path, right? So you cannot find a spanning path rainbow in this coloring, okay? But this result talks about general k-bounded coloring. Now let's go back to Ringel. So in Ringel case, we have a very specific, this Euclidean coloring of the complete graph, which was the union of two factors which came from this putting vertices on the circle and coloring by the color of the distance, right? So this is a specific to bounded coloring. And indeed, by working a little bit more, actually quite a bit more, about 2 years ago, again with Richard and Alexei, we managed to use the properties of this coloring and prove Ringel's conjecture exactly for all large n. So actually, we prove this result gives a little bit more, which actually also was conjectured by Kotzig, that you can tile complete graph. I change parameters here a little bit, on 2n+1 vertices by tree with n edges, right? n+1 vertices. And moreover, you can do it by finding a one copy of your tree and then cyclically shift it. Okay? So again, this is quite involved paper. So obviously I will not have time to talk about this. Let me just say that the proof combines the ideas from this asymptotic result, which I mentioned on the previous slide, as something called absorption technique, which very roughly says the following. So imagine you have your tree, which say has many leaves. Then what you can do, you first delete your leaf to get tree T prime, which is now smaller than n over 2, right? Your original tree was half of the size of the complete graph. Now it's way smaller, right? You gain this little of n. Then you use a asymptotic result to find a good rainbow copy of T prime. And since our proof is random, this copy will have a lot of nice properties. And then we can add the missing leaves back, keeping the copy of the tree rainbow. So that's roughly how absorptions work. And then finally, let me say that a different proof after we publish our result, which doesn't give the cyclic shifts, but gives some other advantages, was found by Peter Kivash and Catherine Steiner. And I think I said all what I wanted to say. So thank you for your attention.
All right, thanks, Benny. That was great. And yeah, you made it even though you started late. So
thank you.
Let me open the floor to questions. Please ask Benny anything you want.
Hi, Benny.
Hi.
It's Jan here. I wanted to ask if you compare Peter and Catherine's result on the Ringel with yours, is there a clear answer which one gives better bound on the n?
No, I mean, the n's are really big, right? So first of all, both Peter and our result uses this asymptotic version. So they also use our tricks to deal with the vertices of high degree. So, and then on top of this, there is an absorption. So the n is, I mean, the n is not as big as in regularity lemma for people who know what I'm talking about, but it's big. It's pretty big.
Okay, sure. Thanks.
Right.
More questions? So many such universality results were proved by, starting from trees and then moving on to bounded degree graphs and so on. They were not about rainbow colors, but they were of the same nature. Do you think that there is a chance to extend this?
So there are even such results. It's a very good question, Avi. So there are even results which shows that, for example, if you take a bounded degree graph modulo, right, and you put and you try to kind of tile it a complete graph. So certain proofs which I mentioned, they extend to the graphs, right? They're more general than the trees. They extend to the graph of bounded degrees. So under certain conditions, you can tile complete graph using this bounded degree graph, right? But then you need to put the bounds of the degree of the graph, right? If you,
right. No, of course, yeah. I'm
right.
just.
So the nice thing about questions about trees that in general they should be true for any tree, right? You don't put any bound.
Yeah, it's the same with some universality results, exactly. Yeah, okay.
Yeah, that's true. That's absolutely true.
More questions to Benny. All right, then thanks a lot, Benny.
Yes, thank you. Hopefully it was all clear.